Hey guys, this question asks, what is the major product of the following reaction? So we are given a compound in a Fischer projection. So this question kind of has sort of two aspects to it. It has a stereochemical aspect. You need to be able to rewrite this compound in sort of line angle configuration to be able to see exactly which atom is where. And then we have to know the reaction. So I'm going to kind of do it the opposite way. I'm gonna start with the reaction first and then work my way backwards to the stereochemistry. So Ki and acetone, when you have two bromines right next to each other like this. So you have a carbon and a bond, another carbon, and you have a bromine on each one of these guys. When you have acetone and potassium iodide, what happens is, well, first of all, these guys need to be in that anti-periplanar arrangement. It's kind of an E2 reaction. It's sort of a type of E2, a variation of the E2. That's the secondary elimination reaction. And what exactly happens is, it's the following thing. The iodine comes and it almost abstracts the bromine the way that a base abstracts a proton. It comes in and it binds to the bromine, and in the process, the bromine's electrons go and form the double bond between the two carbons, while the bromine, the other bromine, gets kicked off as a leaving group. And this is all concerted, meaning it happens all kind of at the same time. And you get your alkene as a product, you get IBr as a product, and you get KBr, because remember we have that potassium still that was floating around with the iodine, and so that potassium will bind to the bromine that just got kicked off, and so then you get potassium bromide. Now, just like any other regular E2 reaction, we have to make sure we take care of the stereochemistry of this reaction, because obviously the way that the atoms and the substituents are arranged will determine what kind of alkene you get in the end. The alkene is going to be stereospecific. So now we go to the first part of the question, which is we have to make sure we draw this out correctly. So the way that you can draw a Fischer projection is as follows. So the top things are going back, and the side arms are coming to the front. I always draw these little bow ties, look like this. And the bromine there. So now I'm going to turn this molecule on its side. I'm going to take this compound and I'm going to turn it this way. So turn it this way so that the CH3 goes here and the propyl goes to the side there. And then once it's on its sort of lying, facing that way, then I'm going to flip it up, because you'll see exactly what I'm going to do. So first I flip it and I get this. Okay. I'll just write PR for propyl. And then here I'll have these guys. So the bromines will face to the front, and the hydrogen up there. There's the other bromine on the top and the CH3 here. And now what I'm going to do is, around this axis, I'm going to flip it this way, like that. And what I'll get is the following. I'll get the carbon and the carbon. And now I'll have the hydrogen will come to the front. So the hydrogen will be a wedgie bond, and the bromine will go in the back, like that. And here's the other CH3. And the same goes for here, except here it's a methyl grouped, like so. And the propyl will be there. So basically I just took this compound and I just flipped it over, just like 90 degrees, like that. Just rolled it over on its side. And I get this compound. Okay, so now I want to get my two bromines in the anti-periplanar position, just like it was here. As you can see, bromine, carbon, carbon, bromine, anti from each other. So let's rotate first this bond here so that the bromine is a straight line there. So I'll get this. So bromine I want there. I want this carbon there. I want this bromine I want there. So when I rotate this bromine up this way, the hydrogen will go down and it'll be up like this. Down and forwards, I mean. And this guy here will go in the back. If you rotate it this way, this guy, the CH3 will go towards the back. So there's the CH3 over there. To get this bromine in the bottom, so basically for this one, I'm just going to switch places. I'm going to say this bromine goes where the propyl is, this propyl goes where the CH3 is, the CH3 goes where the bromine is. So CH will be there, bromine will be there, and the propyl will be here. I think I did the same thing here. The bromine went where the CH3 is, CH3, no, with this one's different because I actually made the straight line up instead of down. So, okay, so this is our compound. When we rotate it now, with the single bonds, we see that we have our anti-periplanar configuration like that. And now you can see that the propyl and the hydrogen is on the same side. Okay, let me just show you there. The propyl and the hydrogen are on the same side, and the two methyl groups are in the same side. So therefore, when we have our product, we will have the alkene that looks like this. We'll have a propyl group, and that'll be on the same side as the hydrogen here. And on this side, we'll have the CH3, the methyl, which is on the same side as this methyl. So that will be our product. Obviously, plus IBr plus KBr. But this is the stereospecific product we get. And let's see which one is that. We want the propyl and the hydrogen on the same side. So therefore, okay, so the product's not going to have a bromine in it, so A is out. As you can see there, A still has the bromine, so that's not correct. B has the propyl and the methyl on the same side, so that's not correct. C has the propyl, or C is just the regiochemistry is incorrect because the propyl and the hydrogen is on the same carbon, and that's not right. D, we see the propyl and hydrogen on the same side, check, and the two methyls on the same side, so yes, D is our correct answer. All right, so you guys should really study this hard. This stereospecificity of the E2 reaction is very, very important. I would really, I cannot emphasize that enough. Make sure you understand that extremely well. Rewind the video and watch it again if you need to. Make sure you are able to understand how exactly we turn the compound from the Fischer projection all the way to the line angle structure, and then make sure that the bromines are anti-periplanar, and thus, you know, we looked at the substituents and how they lined up, and that's how we obtained our answer. All right, thanks for watching, guys.